So we're running a little bit behind on time, so we're going to get started with our keynote speaker, Brendan Burns. He is one of the co-founders of Kubernetes. He is like God to you all. So he's going to be doing our opening keynote today, so let's give a big warm welcome to Brendan.
Cool. Thanks, everybody. Thanks, Kelsey. It's great to be here, I guess. So let's just start it off. As Kelsey said, we're a little short on time, so I'll try not to talk too fast. All right, so I just wanted to take a moment. It was about looking back over the past year of what we've done and where we've gone, and it was actually just about a year ago that I was actually down in San Francisco in a different venue talking about launching Container Engine, the productionization for Google, at least, the initial version of that, of Kubernetes. Since then, and you can see here along the graph, this is our commits to the GitHub repo along the way. Since then, in this past July, we had our Kubernetes 1.0 event where we launched our production-ready version of Kubernetes. I hope some of you were there. It was a pretty good party in Kelsey's hometown. We got Container Engine out to production GA shortly thereafter, and here we are right now. KubeCon, the very first KubeCon, that's awesome. And also I'm going to be talking a lot about Kubernetes 1.1, which is also releasing today. So pretty excited about that. But what I'm actually in some ways more excited about is this, right? This is, and try and find yourself up there if you've committed code to Kubernetes. This is all of the people who have made this possible, right? This is the thing that makes me the most proud about this whole project, is the number of people who have come together to submit code, to work on code, to send us issues, everything else that makes a community, that builds an ecosystem, that creates something that is more than just any one person or any one company, but a really amazing community that's developing around a lot of really cool ideas. So thank you all very much. All right, so that's where we are, and where you are, hopefully. I want to talk a little bit about where we are going, at least where I hope that we are going. And the particular thing that I want to talk about relative to where we are going is why a couple of years ago I even began on this particular journey. And the reason that happened, the reason that I really was excited about this, didn't really have anything to do necessarily with containers. They didn't really have anything to do with scheduling even. It really had to do with this idea that we could make reliable, scalable, agile distributed systems a CS 101 exercise, right? Because the honest truth of the matter is that I suspect most of you don't actually care that much about infrastructure. Now maybe you do, and there are people out there who may actually care about infrastructure, but at the end of the day, we're building applications for a purpose, right? We're building applications to accomplish something, and we want that process to be as easy as possible, as reliable as possible, of course, because if we're successful, people will rely on our software, and therefore our software will need to be reliable. And likewise, we want to make them capable of change, because one of the things that we're doing is we're putting our software out there and we're constantly changing it, we're adding features, we're iterating on it. We have to provide agility and reliability at the same time. It's a very tricky thing. If you were at the 1.0 launch event in July, you heard Eric Brewer talk about how that can be a tricky thing. And really, what Kubernetes is trying to do is make it easier to build those systems in the first place and make it easier to change those systems as well. And so in order to demonstrate that, I wanted to take a brief moment here to go through a demo. And in particular, what I'm going to show you is scaling up to 1 million requests per second in a Kubernetes cluster, and then doing a rolling update of your software across that Kubernetes cluster with no downtime. Right? I'm going to apologize. I was telling Kelsey I felt a little bad about this. I'm going to apologize in advance. This demo is a video. It actually takes about 10 minutes to run end to end, and so you'd be bored, to be honest. So there's parts that have been sped up. But I know everybody wants to see a little blood, so I promise there's live demos later on. All right. Let's go over here. Get this started. Actually, pause. Full screen. All right, so what you see over here is the requests per second on top, our latency number on bottom, our availability there. I'm actually scaling up the load test right now to see exactly how much a single server can handle. And what you're going to see in just a minute is that the latency numbers there in the bottom are starting to creep up a little bit. We're sort of getting up near the capacity of a single server. You can see we have a single web server. In this case, it's Nginx running. Now I'm going to actually scale that up, get the latency number back under control. You'll see latency dropping back down to something reasonable. Because distributed systems are exciting, it takes a little bit longer to get back to stable state than you might expect, but it's back now to under a millisecond at the mean and couple milliseconds at the 99th percentile. Now we're going to scale up our Nginx there to 100 replicas because we want to get to 1 million QPS. We figure each replica can handle about 10,000 requests per second. Now we're scaling up our servers. You're going to see these come online. We're at 100 servers now. We're going to scale up the load now to 1 million requests per second. So you'll see in the upper left there. And again, I'm using replication controllers. I'm using actually Kubernetes to do both the load generation as well as the load handling. And now you can see we're up at 200,000 requests per second on our way up towards 1 million requests per second. So and what you can see here is our latency is just holding steady. Because we figured out ahead of time, we scaled up our cluster ahead of time to reach the capacity we need to get to, we know that we're going to be able to keep our latency number where we want it to be. Going up a little bit, 99th percentile at 5 milliseconds, but that's still pretty decent on our way to 1 million requests per second. All right, so we're at 900,000 requests per second. One more jump in the last little section there. All right, now we're serving 1 million requests per second on our Kubernetes cluster, right? Now, what the really exciting thing is, 1 million requests per second, honestly, it's actually not that exciting. We did it about a year ago on the Cloud Load Balancer. What's really exciting is the ability to roll out your software with no downtime while doing 1 million requests per second. So you'll see right here, I'm doing a rolling update using kube control to do a rolling update from an old version 0.2 of my software to version 0.3 of my software. Sorry, I got clipped off a little bit there. And now what you're going to see here is the rolling update in progress. And as you can see in their server availability in the lower left, this is the part that's been sped up. We're staying at 100% while we're rolling from the old version to the new version of our software. You can see the 1 million requests per second still running there. All right. And there we're done. 1 million requests per second, updating your software without any downtime. And that's really what we're about, right? That is, in a nutshell, what we want to be able to do. We want to make software available to everyone, easy to build, and reliable to change because we know that software is constantly changing. The easiest, most reliable software out there is just like a for loop, right? It's not doing anything. It's not very exciting, though. We want to be able to change our software. We want to make our software something that is alive. All right. So go back into presentation mode. And I wanted to talk a little bit more about how that demo is constructed. So what you can see here is the basics of how you build out 1 million requests per second inside a Kubernetes cluster. Well, you have a bunch of replicas of the Nginx. You have a replication controller that's driving those replicas. We have an Nginx service that's in front of that replication controller that gives our load testers a target to target. And we have a loadbot replication controller as well. Now, what's important about this is that we're all running inside the same Kubernetes cluster. Now, when you start reading about load testing and things like that, oftentimes people say things like, well, don't run your load test on the same machine as you're running your server and this sort of stuff. And the truth is that actually in Kubernetes, it doesn't matter. The resource isolation that our containers provide allows you to run the load test right alongside the things that are doing the serving. Now, but what's interesting is you do this load test and you realize actually you have to scale out your load bot to have 1,000 of these iterations is you actually have to do some work to do the data collection to actually produce that pretty graph that you saw. So in addition to the actual load that's being laid down, I actually had to build this data aggregator. This data aggregator actually talks to the Kubernetes API to go and find the pods where the app is load bot and aggregate the data. That means as I scale out my load test, I dynamically update the people who I'm collecting data from. I didn't have to program my aggregator to go and find these things by itself. It just uses Kubernetes as the service to do that. And again, this is the part where we're making it easier to build distributed systems. And then, of course, we use a service on top of that data aggregator so that we can have our GUI know where to find, no matter where that pod ends up in our cluster, we can have our GUI that displayed those graphs know how to find the data aggregator that it needs in order to do the visualization. All right. So I think hopefully that gives you an idea both of the kinds of applications that you can build on top of Kubernetes, the way that you can use Kubernetes both to serve your load as well as to produce your load, as well as use the primitives inside of Kubernetes to make it easy to build systems. But this is all built on things that we have built so far. These are all built on things that were in Kubernetes 1.0. And so what I want to turn to now is where we go from here, where we go today and where we go into the future. And starting from today with Kubernetes 1.1, we have a bunch of new exciting features for you, and I want to walk you through them. All right. so in no particular order, we are adding HTTP load balancing, auto-scaling, batch jobs, resource overcommit. Kube proxy is now based on IP tables. It's optional. You can choose between user mode and IP tables, and we'll talk a little bit about that. We added a whole bunch to kube control. It's pretty awesome. You see how we can do 1 million QPS. We're going to see some talks later on about people who are running 1,000 node clusters and much, much more. So it's a pretty awesome release. We're really excited for everyone who put a lot into it. We really appreciate your patience, because it's a couple weeks late from when I originally promised. We are still working out the kinks of how we release software on a cadence, as it turns out. We promise 1.2 will be on time. Well, I hope. All right, so it's out today. It's going to go out to Google Container Engine this week, to new clusters. We're going to give people some time to test it out in Container Engine with new clusters, and then we'll be doing automated upgrades for existing customers of Google Container Engine out to 1.1 in a couple of weeks. If you want to in earlier on that, because there's features you absolutely have, send us a note. You can either send us a note and say, I want to be on the bleeding edge and be one of the clusters you test with, or you can say, you know, I want to be early, but could you test on somebody else first, and we'll make sure that that happens. All right, cool. So then, without further ado, I wanted to step you through the details of all of those features. All right, so the first is HTTP load balancing. Now, previous to this release, this is how you had to set up your cluster, right? We had load balancing, but it's layer 3 load balancing. And if you wanted to serve 2 different services, you actually had to expose them on 2 different IP addresses. And if you wanted to have something like path-based load balancing, you actually had to roll that yourself. So this is the bad old world of Kubernetes 1.0. And this is how we're going to change things. And the API in particular for HTTP load balancing is called ingress. And so this is what it allows you to do. It allows you to create an ingress point, api.company.com, and you can actually set up paths that map to your services. So you can say api.company.com/foo maps to this service, api.company.bar maps to this other service over here, right? So this is the idea that there's a place where all your packets come in, that's the ingress part, and then there are the paths that lead out to the various services that you're implementing in a microservices approach to constructing your architecture. All right, so that's the ingress API, as I said. All right, so I want to give you a little bit of an example of what we can do with this. So the first example of this is exactly what I just showed before, and here's the API object on the left there. And this shows you can say, okay, for a particular host, in this case k8s.io, you can map foo to one service and bar to another service. But that's not the only thing that people may want to do. You may actually want to do something like this, where you want to map everything from k8s.io to one service and everything from j7a.io to another service. j7ia being what I type accidentally sometimes when I'm going to k8s.io. And so you can see here the API object is similar, but it's a little bit different. We have 2 host entries with a single path. Previously we had, if I go back, we had a single host entry with multiple paths. And of course, you can mix those together, right? And so you can say, I want to actually have multiple hosts, each with multiple paths, and map them out to different services as well. All right. So when we want to implement ingress, well, those of you who've been around me long enough know that the favorite approach to doing anything inside of Kubernetes is a controller. Someday, I'm hopeful that we'll have a controller. Well, actually, we sort of do have a controller, but we didn't call it a controller. But maybe we'll have a controller in good Java style. But this is how we implement ingress. There's this ingress object. It's in the API. And then there's a bunch of ingress controllers. We've built one out for Google Compute Engine that manipulates the Google Compute Engine HTTP load balancer. There's one in development that the pull request is out for HA proxy so that you can develop these HTTP load balancers that are implemented using HA proxy. We anticipate the community, that's you all, are going to develop a bunch of these different ingress controllers. So the ingress object exists as a Kubernetes object. The controllers that are for GCE and HA proxy and whatever else you want to do for HTTP load balancing are going to be individual modular entities that you can deploy and choose which one you want depending on where your cluster is and what works for you. All right, so that's ingress and the HTTP API. The next feature that I'm extremely excited about, and a little bit of a shout out to the team in Warsaw for building this, is horizontal pod autoscaling. And I note that it's beta. I should have mentioned with ingress as well. The new APIs, ingress, autoscaling, and the job API you'll see in a bit, they are all in beta. They're all ready to go. We believe that the API will remain stable, and we are going to make sure that even if it changes a little bit, you have the ability to move forward, but they are new APIs, so use caution depending on where your production tolerance is. So this is what horizontal pod autoscaling did. Previously, when I created one of these load balanced services, I had to be at the controls, manually scaling up or scaling down depending on the load that I might expect. And that's okay, if you sort of have predictable load or you're willing to be awake all the time to scale things up. But what you really want is a robot. I have my PhD actually in robotics, so I was telling Kelsey, he didn't mention before. I actually have 3 robots in my basement. They do not adjust auto-scaling, although it'd be pretty awesome if they did. So you really want a robot to be doing your scaling for you. And with the Kubernetes 1.1 release, now you do. Every single one of you, when you deploy Kubernetes, have your very own robot. All right, so this is what horizontal pod autoscaling looks like. You can see here, it's the autoscaling resource. It takes a pointer to a replication controller. It's actually a scale reference. The reason it's a scale reference is because anything that implements the ability to be scaled can actually be scaled by the autoscaler. Currently, that's replication controllers. And then there's a configuration information for the robot, like what's the minimum number of replicas that I want? What's the maximum number of replicas I want? What's the target percentage for CPU usage? The autoscaler supports CPU utilization as well as memory utilization for scaling. Hopefully in the 1.2 timeframe, we'll be able to have custom metrics available to you. But this will allow you to scale your replication controllers in response to the load that they're seeing rather than having to have you manually scale things up and down. All right. Many of you may be asking, but why is it called horizontal? We like to have lots of words in our API names, but we didn't throw it in just out of interest. So I wanted to take a minute to sort of describe why we call it horizontal and give you maybe a flavor of where we're going in the future. In particular, we call it horizontal because the way that it scales things is it creates more pods. It creates or reduces the number of pods. So if you imagine your pods laid out on an axis, it's horizontally scaling the number of your pods up and down. But of course, this isn't the only way to scale things, right? You can actually scale things vertically as well, right? And we don't do this currently, but it's definitely a point of interest to figure out how we can scale your pods, not just horizontally, but also in terms of the amount of resources that they use, right? So vertical autoscaling adjusts individual pods' resource usage. Horizontal autoscaling adjusts the actual number of pods. It's going to be pretty cool. All right, so the last API that I wanted to run you through pretty quickly is the Jobs API. So this is a classical web service. It runs all the time. That's not what the Jobs API is about, right? So previous to this, Kubernetes was pretty good about running long-running services. But if you wanted to run batch jobs, you had something like a transcoding that you wanted to make absolutely certain ran to completion, it was a little bit awkward. It's possible, but it was definitely a little bit awkward. And the Jobs API is the beginning of an effort to make those sorts of workloads work nicely and natively inside of Kubernetes. The whole point of the Jobs API is to get something from start to finish, right? Okay, so that's the basics of job, but I want to talk a little bit more about the details. You see here the Jobs API object. Maybe it's doing FFmpeg. It's running a single thing from start to completion, right? It has things that you may expect from replication controllers, like a restart policy of on failure. It defines out the template for the pod that will be created, everything else like that, label selectors and everything else you'd expect from a Kubernetes object. But it has some added things, right? You can actually say things like, how many completions do you want? Do you want this thing to run only once, or do you want it to run to completion 5 times, or 10 times, or 1,000 times, right? So completions tell you the number of times you want something to run, and by default, all of those things run in parallel, right? So if you ask for 5 completions, you're going to spin up 5 pods in parallel. They're all going to run, and they're going to run till they finish. But sometimes you want to be able to say, like, oh, actually, I have this whole thing. I want to get it done, but I don't want to take up too much of my cluster. Maybe I only want to take up a certain percentage of my cluster at a time. And so in order to do that, we add a notion of parallelism, right? So you can say, I want to run to completions 5, but I only want parallelism of 2, right? And so that means that I'll run 2 things to completion. When those 2 things are done, I'll run 2 more. And then, of course, to get to my 5th, I have 1 more, right? So this enables you to have some flexibility about how many times you want to run it and how parallelized you want them to run. All right. And so jobs are really the foundation of a whole bunch of workloads, from things like scheduled jobs that can implement cron, to things like workflow, more detailed sort of Rube Goldbergian things. We're going to be adding features to the Jobs API as well to make it more useful, like automatically providing you with shard numbers so that if you say, like, I want 10 of these things, one will get shard 1, one will get shard 2, one will get shard 3, so that you can split up your work without having to do very much on your own. And again, this is back to the beginning where I said what we really want to do is make it easy to build distributed systems, right? We will take care of the orchestration and the management of it. So these are all things that are coming into the future, but the jobs object that's part of Kubernetes 1.1 is the foundation for all of that. All right, so I hope you're excited. Just to summarize, the three new APIs that we've added to Kubernetes in the 1.1 release: HTTP load balancing, horizontal pod auto-scaling, batch jobs. But that's not the only thing, right? We don't just add APIs. We actually want to make the system better as well as we're doing, adding new things. We want to be investing into the core infrastructure as well. And I wanted to cover a little bit of that too, right? A little bit of the work that people have done over the time. The first one I want to cover a little bit is resource overcommit. All right, so with resource overcommit, and in particular it's memory overcommit, we have the ability we define essentially 3 classes. We have a guaranteed class where you are guaranteed the resources that you want, a burstable class where you have a certain amount of you have a certain lower level of resources, but you can burst up to higher level resources, and best effort, which is, as you might imagine, best effort, right? And in particular, this is the way that it works, right? When you ask for something, when you define a Kubernetes pod, you define the resources that it needs to consume. And there are actually 2 different kinds of resources that you can specify: the request and the limit. Request is how much you want. A limit is the maximum that you can use. And so if you ask for a request that is the same as your limit, you're in the guaranteed resource class, right? You're guaranteed to get the amount of resources that you need. If you ask for a request that is less than your limit, you're in the burstable class. You're guaranteed, you have the 5 gigs of memory that you've requested there, but you might burst up to 10 gigs. And then finally, if you're in best effort, you just ask for a limit. Right? You just say, this is the maximum I want you to use. And in particular, what this means is when the system is over-constrained and the system runs out of memory, things that are in the best effort class are going to be the first to die. Right? And so this enables you to overcommit the amount of memory that's on the machine, pack more things in tightly, but still have good control and insurance that the things that you really care about are not going to be the things that the system kills when it is over-constrained. All right. So the second thing, and this is a feature that I know a lot of people, this is probably, I don't know if it's the most anticipated feature for 1.1, but it's definitely a big thing for people. We're replacing the kube proxy, we're optionally replacing the kube proxy with an IP tables-based implementation, right? So previously, the proxy for all the services inside of Kubernetes was a user space daemon. With Kubernetes 1.1, you can choose. You can choose an IP tables-based version, which is, again, like horizontal auto-scaling and everything else like that. It is in beta, and so use it with your discretion. Hopefully we'll graduate it from beta to being the only implementation with the 1.2 release. But just to give you a flavor, there's 2 really big wins that you get from the IP tables-based load balancing. The first is that source IP addresses are going to be preserved. Right? So the user space load balancer previously just did end-to-end TCP connections, and the source address was lost. With IP tables, source address will be preserved. But more also, a big part of this is that the latency, and this is a histogram of latency. Blue is the IP tables-based version. Red is the user space version. A couple things to point out. First of all, the user space version doesn't even get off the ground until about 110 microseconds there. Right? Doesn't even start handling requests. And actually, the IP tables-based version has already served a very significant proportion of the requests even before then. Also importantly, you'll see that the long tail, and in particular, it's a little bit hard to see, but there's actually a really kind of nasty tail spike out at the end there of tail latency that's due, I think, to garbage collection inside of Golang. That goes away entirely. So latency is reduced overall. The fastest you could possibly expect is reduced significantly, and in general, it's just a better solution. But we want to give it some mileage. We want people to get out there and use it before we declare it the GA solution. But I'm pretty excited about that, and thanks to the intern over the summer who made that work. I think it was an intern. It was either Google Summer of Code or an intern who made that work. All right, and then finally, we have some improvements to kube control as well. So we've added interactive modes to kube control. So you can say kube control run -i tty You can give yourself a shell, and that will give you interactively a shell inside of your Kubernetes cluster. You can use it to do, wget or nslookup or whatever it is that you want to do to be able to debug your cluster. You can also attach to existing containers that are out there in your cluster. So you can go out and, again, get an interactive attached shell to a container that is already running. We've added kubecontrol edit that allows you to take an existing API definition, download it onto your machine, kick it up into an editor that you choose. I'm not going to choose sides in the whole VI Emacs thing, but kick it up into your editor of choice, and then edit it, and then submit it back into the container, into the cluster, right? So that's a really nice, easy way to interactively edit what's going on. And finally, kubecontrol apply, which is really a way to take a set of API objects and ensure that they are added and into the, or that they are accurately reflected into the cluster. So I definitely encourage people to look into those. They're really awesome tools to make it easier to manage applications that you're running inside of Kubernetes. All right, and then finally, we've made a bunch of, you just saw rolling update in the demo, and we've actually made a bunch of improvements to rolling update. In particular, we now wait until your pod is completely healthy before we move on to the next one. That's pretty awesome. We really should have done that in the first version. Sleep 20, right? I mean, what could go wrong? So we actually look at the pod's health and the pod's readiness state before we upgrade before we move on to the next pod that we're rolling to. So we're good now. We also look at terminal failures. So if that pod just never comes up and it never comes up correctly, we'll actually pause the rolling update, right? So if for some reason the rolling update is in process and it dies, or the new version that you're rolling up to just dies and won't come up, we're going to pause the rolling update. You'll have an opportunity then to investigate, see what's going on. And of course, rolling update has that -- rollback flag, which will allow you to immediately roll back whatever version you happen to be doing. So, all right. I'm just going to do a quick time check. All right. So that was Kubernetes 1.1. I hope that's fun. I'm pretty excited about it. There was a lot of effort that went into this release across a bunch of people. And so it's available. It should be up on GitHub as we speak. It's going to be rolling out to Container Engine over the course of the week. So, all right. So now I wanted to take a little bit of a step back and talk a little bit, and this is where maybe I get up on the soapbox a little bit. Talk a little bit about where I want to see us going, right? And you should take this with a grain of salt. This is really me talking about what I'm excited about and the ideas that I see going forward. The future is uncertain, and we'll see where we end up. Okay. So I said this earlier, but why are we here? It's not to run a lot of containers. It's not even to run containers, I don't think. It's to build applications. It's to update those applications. It's to operate those applications reliably. And to do it all easily, because at the end of the day, we want to focus our energy on the applications that we're building and the users that we're making products for, not the infrastructure on which it runs. All right. So I want to take a moment and think about how we have been thinking about distributed systems and how we might think about distributed systems. And in particular, I want to take a hypothetical and say, what if we thought about writing distributed systems exactly like we wrote applications? And in particular, I want to take the example of leader election and master election as that example, right? And what you see here is a really simple type definition. A leader function gets a isLeader, it's a Boolean, and the current leader's name. And a leader elector, that's an interface that says install leader function. All right? That's an easy to implement thing. You can easily imagine programming this into a binary. Right? It might look something like this. Here's your leader function. If you're the leader, you get to print I'm the leader. If you're not the leader, you print who the leader is. All right, and you could easily imagine turning this into a program, create a new elector, install the leader function, run that elector. Right? This is all not particularly fancy and not particularly revelatory, but what I want people to think about is, what if this isn't just a process that's running on your machine? When you compile that binary and you run my leader elector, replicas 3 in daemon mode, what if it's actually talking to a Kubernetes cluster? And what its job is to do when you run that program is actually to bootstrap itself up into that cluster. To do all of the necessary things, to create 3 replicas of etcd, to create 3 replicas of the program, to introspect the file system, find the program that was compiled to, get it up into your Kubernetes cluster, and actually run that leader election program up in the Kubernetes cluster. Now your development experience is, I wrote this code, I compiled this code, I ran this program, But what happened in actuality is that program is now running out on a distributed system, running as a distributed system, right? So everything that we're used to, everything that we think about in terms of development is the same as it ever was, but the net effect of where it runs and how it runs is fundamentally different. So this is something that I'm really interested in exploring. This is very speculative. I've started to write this code, and if people are interested in moving forward with this, please come talk to me today or in the future. All right. So then the final thing I wanted to talk about briefly is looking ahead to Kubernetes 1.2. We just managed to get 1.1 out the door, but I wanted to take a moment and think about what are some of the themes and what are some of the things we're thinking about for Kubernetes 1.2. All right. So one thing I'm really excited about is the notion of pre-built applications. So I don't know how many of you saw, we've open sourced Deployment Manager, which is a sort of higher level orchestration tool. It's available up on GitHub. Deis announced this project called Helm. It's pretty awesome. Go check that out as well. And I think this is really going to be the theme. If you want to think about something that's going to be happening, and I've said this before, but if it's sort of like containers and then orchestration and now applications, that's I think the progression, right? Because at the end of the day, that's what we want to run, right? We don't want to run, as I said, individual containers. We don't even want to run replicated Nginx. We want to run whole-scale applications that do interesting things. So I think this is going to be a really interesting area of development. I'm excited to see where this goes. All right. We're also very interested in cross-cluster management. So people have seen Kubernetes. Kubernetes is sort of the general umbrella initiative for how do you manage multiple clusters? How do you manage applications that span multiple clusters? I think it's probably, once everybody turns up their first cluster, like the second cluster is the thing where they say, oh, wait, I need something now to manage multiple clusters. How do I share services between these clusters? How do I have a unified visual dashboard to all of these things? And I think this is an area where we know we are going to be doing more exploration. We don't have all the answers, and this is why I want the TBD is up there. Someone actually said, you should probably edit out the TBD before you show these slides to people. And I was like, no, the point is, we need input from the community. I want people to come and tell me what they need, and we can build the tools that make it easier for you to manage multiple Kubernetes clusters. All right, and then finally, we really want to work on simplified config, right? We want to work on template, and this is an example, but I wouldn't take this as, this is more of an inspirational example than a concrete syntax yet. But what we really need to work on is tools that make it easy for people to establish templates, to establish generators that can take simplified config files and turn them into Kubernetes objects. And this is definitely also something that we're going to be working on in the time frame to Kubernetes 1.2. And so if you're interested in any of these things, please come and talk to us. Please come to the community meeting. Please come and put issues on GitHub. Just like with 1.1, we're going to be establishing a 1.2 milestone. Feel free to create issues and put things into that milestone. Please don't be upset if we then take them out. We have to prioritize a bunch of people's interest and use cases, but please come and participate in that process. All right, and thank you so much. I'm excited that you're here. I hope you have a wonderful time. I'm going to be around all day today. Come find me if you want to chat. Thank you very much.